Jai Hind, welcome to class of Analog and Digital Communication. We're going to talk about pulse modulation. So, this is a lecture preceding, which is in continuation with the previous lecture, where we have already discussed the basics of pulse modulation, right? So, to give you a brief overview of what modulation is. Modulation is the process of altering the characteristics of a high frequency carrier wave with respect to instantaneous value of the message signal, right? So in case of pulse modulation, the high frequency carrier that we consider is not a sinusoid, it is pulse in nature. So high frequency train of pulse, when we consider as a carrier wave, that kind of modulation is called as pulse modulation. Although this is an intermediary stage between our analog communication to digital communication, whenever we want to convert our analog wave into digital wave, there are certain steps that we have to follow, which are sampling, quantization, and encoding. So sampling has been discussed in detail in the previous lecture. So based on sampling, we can generate certain modulated waves. So pulse amplitude modulation is one of the examples. So what is pulse amplitude modulation? This is a kind of modulation where my message signal is analog in nature and the carrier which I consider for modulation is a high frequency train of pulse. And when my continuously varying voltage signal converts the amplitude of my high frequency train of pulse, the samples that I get as output are called as pulse amplitude modulated waveform, right? So here I can say that if my message signal is a continuous wave and the carrier which I consider for modulation is a high frequency train of pulse, and if this continuous wave is able to alter the amplitude of this high frequency train of pulse, then the output waveform that I obtain is called as pulse amplitude modulated waveform. So PAM is a kind of modulation which comes under analog modulation, having a pulse carrier as a carrier wave. So let's get back to the tree. Under pulse modulation, we had analog modulation and digital modulation. So if I talk about analog pulse modulation, then PAM, pulse amplitude modulation, pulse width modulation, and pulse position modulation, these are the three kinds of modulation that we should be talking about. So in today's lecture, we are discussing about PAM in detail, right? So to reach this stage, that is to obtain pulse amplitude modulation, there are certain steps like sampling, which we have covered in our previous lecture, right? So pulse amplitude modulation, it is the simplest form of pulse modulation. In this type of modulation, each sample is made proportional to the amplitude of the signal at the instant of sampling, right? The PAM signal follows the amplitude of the original signal as the signal traces out of the path of the whole wave. Here, a signal which is sampled at Nyquist rate can be reconstructed by passing it through an efficient low-pass filter. We know what is sampling at Nyquist rate. When we sample a wave at a rate at a lowest sampling frequency, that when we keep fs equals to twice of maximum frequency content of message, then this sampling at this rate is called as Nyquist rate. If we sample at this rate, then it can be reconstructed by passing through an efficient low-pass filter, which is a well-known fact, right? With exact cutoff frequency. Now it is very easy to generate and demodulate PAM signals, right? This is the technique that transmits the data by encoding the amplitude of a series of signal pulses, right? So we can consider a pulse amplitude modulation as a kind of modulation where signal is transmitted in the form of uh, amplitude modulated pulses, right? So we can consider our PAM signal as an encoded version of signal where it is it passes as amplitude modulated samples, right? So this is how my PAM signal should look like. If this is my continuous wave, which is my modulating signal or the message signal, and the carrier which I use is a high frequency pulse train, then my my pulse amplitude modulated signal must look like this. That is, the amplitude of my pulses will vary with respect to the instantaneous value of my message signal. When the voltage is rising, the amplitude of these pulses keep rising, and at its falling edge, the amplitude falls. So if I plot it using some reconstruction thing at the receiver, I would be able to retrieve back my message signal. So this is how my PAM looks like. Now the question is how to generate pulse amplitude modulated signal. For that, we need to understand how sampling takes place and what are the various types of sampling, which we have covered in the previous lecture. Sampling is the process of converting a continuous time signal into discrete time signal, right? So sampling is of three types, which is my instantaneous sampling, flat top sampling, and natural sampling, right? So if we remember, this is how we represent our instantaneous sampling, right? And this is how I represent my natural samples, and this is how I represent my flat top samples. So from here the relation could be derived that PAM is nothing but simply generation of flat top samples, right? So if I am able to generate flat top samples corresponding to some message signal, then I would be able to successfully generate my PAM signal. So for that, what kind of circuit I need? For that, I need a circuit that will sample at a particular voltage and hold that value for sampling time interval, right? So I need a circuit, so that kind of circuit is called as sample and hold circuit. Let us give a look again to this. I need a circuit that would plot the amplitude value in proportion to the modulating signal, hold it for the duration for which my sample appears, and then release it. Then again it should take the next sample after TS, that is sampling time interval. This is how my circuit must work ideally, right? So that kind of circuit as per the NEET is called as sample and hold circuit. That should be able to sample, right, my signal at a particular value and hold the sample for a particular duration, and this process must be repetitive, right? So such kind of circuit is called as sample and hold circuit. A sample and hold circuit, what is it? It is an electronic circuit which creates the sample of voltage given to it as input, and after that it holds these samples for the definite time. The time during which sample and hold circuit generates the sample of the input signal is called as sampling time, which is true. Similarly, the time duration of the circuit during which it holds the sampled value is called as holding time, right? The time gap between appearance of two samples is called as sampling time, and the time gap time duration for which it holds that particular sample is called as holding time, right? it will not be wrong to say that capacitor is the heart of sample and hold circuit. So before coming to this point, we need to see the circuit diagram. This is how my sample and hold circuit must look like. It should be having combination of amplifiers, a switch and a capacitor, right? So from here I might give an analog input, right? And what value passes then depends on the switching time, right? At what moment this switch closes, it closes at every ts time duration, right? So it closes as per my this timing should be maintained as it must be integer multiple of every sampling time duration, right? So it closes at ts time, and then that particular voltage level is picked, right? And as per that my capacitor charges. Now this capacitor must charge quickly and must hold the charge for the duration for which my sample must appears, and it should it should quickly discharge when uh, 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 quickly discharge after that time duration for which the sample must be held, and again the switch should be closed at next sampling time interval, right? So let's give it a look. It will not be wrong to say that capacitor is the heart of the sample and hold circuit. This is because capacitor present in the circuit charges to its peak value when the switch is open, that is during the sampling, and holds the sampled voltage when the switch is closed, right? So I give input, this close it at every sampling time interval, that up to that voltage the capacitor charges, and it holds the charge up to the duration the sample must hold. After that this switch closes and it discharges, right? And while discharging, the next charging should start after the appearance of my after the appearance of my next sample, which should be delayed by ts time duration. So I can justify it with this, right? So uh, this circuit works for generation of sample and hold waveforms, right? So when I give input, the sample and hold circuit must give V output, and I can say at this voltage this is called sample, this is hold, and sample, then hold, sample and hold. That's why this circuit is called as sample and hold circuit. With the help of sample and hold circuit, we can take samples of analog signal which are followed by a capacitor. It holds these samples for a particular period, and as a consequence of this, a constant signal is generated which can be converted into the digital signal with the help of analog to digital converters. True. Now, what are the advantages of my PAM signal? Both modulation and demodulation are simpler here. The construction of transmitter and receiver is easier here. And if I talk about what are the disadvantages, it requires large bandwidth. Transmission bandwidth required for PAM signal is too high. So as the information is contained within the amplitude, so it must be noisy. It is very noisy. Here the amplitude is varying, therefore the power required will be more. It is a difficult task for transmitter to keep varying its power. We know that at this voltage the power required will be different, at this voltage the power required will be different, right? For a constant voltage signal, the power that should be transmitted is fixed, but here the transmitter has to constantly keep changing its power level, which is not a very good thing for a communication system, right? So noisy and power variation, these are two of the major points, and bandwidth requirement, larger bandwidth requirement is also one of the major reasons for which we avoid using PAM signals in our communication. Okay. What are the applications of PAM? We use it for Ethernet communication. Many microcontrollers use this technique in order to generate control signals. This is also used in photobiology, It also acts as an electronic driver for LED circuit. These are some common applications of PAM signal, right? Another pulse amplitude, another pulse analog kind of modulation is your pulse width modulation, which is also called as pulse time modulation, right? Here what will happen, as the name suggests, corresponding to this message signal, the width of my pulses will vary. This is my normal carrier, but as the voltage rises, the width will be varying. Like at this peak, my pulse will acquire maximum width, and for preceding, when it is decreasing, the pulse width will decrease, right? Here the pulses will have the same amplitude and same frequency. Number of pulses appearing per unit time will be same. The amplitude of the pulses will be same. However, the width of the pulses will vary. How does it vary? This variable characteristic can be either frequency, position, or width. Here what we are considering is the width. When the pulse is having variable width, we can also say that it is sustaining for a variable amount of time, right? So we can either call it pulse width modulation or pulse time modulation. Pulse width modulation is also known as pulse duration modulation. Here the name suggests the width of the pulse is varied in proportion to the amplitude of the signal. So we may either call it pulse time or pulse duration or pulse width modulation. Since the width is changing, the power loss can be reduced when compared to PAM signal. Why power loss can be reduced? Because in PAM the power is continuously varying because of the variation of the amplitude. Here there is no variation of the amplitude. Let's see how PWM waveform looks like. If this is my modulating signal, this is how my carrier signal looks like. But here the carrier, the width of the carrier will increase or decrease as per the modulating signal. Modulating signal is always considered to be a voltage signal. So when the voltage is rising, the width will increase, the voltage is falling, the width will decrease. And we can assume minimum width at this point, this, and we can assume the maximum width at this point of time, right? We can see the difference here, right? Here the information is contained within the width of the signal. What are the advantages? It consumes low power, it has efficiency about 90%, which is great. Its noise interference is less, it has high power handling capacity. And if we talk about the cons, disadvantages of pulse time or pulse duration or pulse width modulation, this circuit is more complex. Voltage spikes can be seen, and the system is inexpensive as it uses semiconductor devices. Even the switching losses will be more due to high PWM frequency. What are the applications of pulse time modulation? It is used in encoding purposes in telecommunications. It is widely used, right? It is used to control brightness in a smart lighting system, which is great. It helps to prevent overheating of LEDs when maintaining the brightness, which is also a very good feature, right? It is used in audio and video amplifiers. Next is pulse position modulation. What is position modulation? As the name suggests, here neither the amplitude nor the width will vary, whereas the position of the pulses will vary with respect to the voltage signal, which is my modulating signal. Now, in this type of modulation, both the amplitude and width of the pulses are kept constant. We vary the position of each pulse with reference to a particular pulse, true. Here, a single pulse is transmitted with the required number of phase shift. So, we can say that pulse position modulation is an analog modulation scheme where the amplitude and width of the pulse are kept constant, while the position of the pulse with respect to the position of a reference pulse is varied according to the instantaneous value of the message signal, right? So let's see how it looks like. So this is a well-known fact that we cannot just simply draw pulse position modulation considering my message signal and carrier wave. For reference, we do have to take PWM, pulse width modulation. This PPM can be obtained from PWM, not directly from message and carrier. This is done by getting rid of leading edge and bodies of PWM pulses. This is the main advantage of pulse position modulation. It requires a constant transmitted power output, as there is no voltage or amplitude variation, while the major disadvantages, it depends on transmitter receiver synchronism, because when position varies, how your receiver receives the signal, they should be perfectly synchronized, otherwise there will be mismatch and loss of data. Let's see how the waveform looks like. If this is my modulating signal, this is how my PWM looks like. When the voltage is varying, I have maximum width pulse. When this is minimum, I get minimum width voltage. When this is maximum, I get maximum. Likewise, what happens in PPM? The position to vary the position, what we have to consider the falling edge of pulse every time, taking the reference of PWM. At every falling edge, draw a pulse of similar amplitude and similar width as that of the carrier wave, as that of the carrier pulse. So at every falling edge, you draw a pulse. Again, at this falling edge, you draw a pulse, and automatically, as the width of the pulse was varying in PWM, you get a position shift every time, right? And from here to here, you again get some position shift, right? At every falling edge, you draw a pulse. At every falling edge, you draw a pulse of similar amplitude and width as that of the original carrier. And this is how you may obtain PPM signal. What are its advantages and disadvantages? It has a constant amplitude noise and noise interference is less. We can easily separate signal from a noisy signal, and among all three types, it is most power efficient. Why? You don't have to keep the signal on for longer duration as in case of PWM, right? You don't have to vary the power levels as there is no amplitude variation as in case of PAM. Like in PAM, because of such structure, power variations you get, so average power is high. In PWM, you have to keep the power on for longer duration of time when the width of the pulse is larger, whereas in PPM, only the position is varying, neither the amplitude nor the width. So power is fixed. You don't have to keep power on for longer duration of time. So this is the most efficient form of a pulse modulation if we compare these three versions, right? This is a clear-cut advantage of using PPM. Among all three types, it has the most power efficiency, true. Requires less power when compared to pulse amplitude modulation, true. What is the disadvantage? It's a highly complex system. You cannot directly get signals, so your system has to be little complex. The system requires more bandwidth. This is another major disadvantage. What are its applications? PPM is used in air traffic control system and telecommunication system. It is also used in remote controlled cars, planes, trains, which uses your pulse code modulations. This is what we'll discuss later. It is also used to compress data, and hence it is used for storage. So PPM has got so many applications, right? So these are the references which I have used. Thank you.